All right. Let me just take a quick look to be sure. Yeah, we got through all the slides. Now we're going to take a look at the review. And this review is for Exam 5, Chapter 9, Chemical Quantities. And that exam will be Thursday. And like I always do, I open the floor for burning questions first, so we can get you guys covered before I start talking. So,
how come you got number 9?
Actually, there are more than one. More than okay. When I first put this thing together, I wrote out worked out the problems like that, and I went back and looked at some of them, and those that I left blank covered material that's not in this chapter. You know, I was using the author's questions to work from. You know, they have a test bank. So I put that test bank together and then work out the problems. And then I went back and looked and said, wait a minute, we didn't cover that stuff yet. So since I'd already done this document by hand, the only way to keep them in sequence was to go back and do the whole thing over again. So I just went in and X'd out those in the worked problems and did what I did here. That seemed like the easier way out. Okay. Nothing particular burning a hole in your brain?
I like 76.
76? Okay. Let's see how much.
So there's a lot.
Yeah, let me just make a note down here so I don't forget. We're going to get to 76 eventually. Let's look at some simpler ones first. How about number 2? I want to start off slow and build up steam. For the reaction, 2 sulfurs and 3 oxygens yields 2 sulfur trioxide. Okay, there's our balanced equation. And you can check it to be sure. 2 sulfurs, 6 oxygens. Yeah, we're balanced. The question is, how many moles of sulfur trioxide? How many moles of that one will be produced from 2.2 moles of this one? Okay. So first question you ask yourself is, can I go from one place to the other with the information I've got? The answer is yes, because you're already in moles. Right? If it's not in moles, you have to convert to moles, because the relationship in the balanced equation is all numbers, not mass, not volume, numbers. Numbers means moles. So we've already got moles, that's great. So how do we convert from that to that? Because now that we have moles, right, we can cross the barriers. So not skipping any steps, that many moles of oxygen is where we are, and this is where we're going. Moles of this one. Okay, so we're headed there. This is where we're coming from. Okay, that cancels the oxygen and leaves us with sulfur trioxide. I left out the moles in here hopefully you understand. But so the ratio here comes from where? The coefficients. So we have 3 oxygens for every 2 sulfur trioxides. Now we can cancel the oxygens and take 2/3 of 2.2. Go. 2.2, and I get 1.47. Or rounded off 1.5. Let's see what the answers are. 1.5. So it did round off to 2 significant figures. Okay. So after you've got a balanced equation, you have a whole bunch of conversion factors available. Just which one do you need? Conversion factors, moles to moles, are related to these coefficients. Now these have numbers there that are actually written in. If there's no number there, what's the coefficient? 1. Okay. I think we're good there. All right, that was number 2. Let's do number 3. In this case, we're given a balanced equation. We're also given absolute amounts of reactants. Okay. So we're adding to the complexity of the problem. We've got 2 sodiums and 2 water. Yep. We got 2 sodium hydroxide in solution plus hydrogen gas. So you're going to see some bubbles out of this reaction. You're also going to see a lot of heat. When you throw a chunk of sodium in a swimming pool, you get lots of heat. It's a violent reaction. But that's beside the point. What are we given? Well, the question is, what number of moles of hydrogen will be produced? So that's the question. From 4 moles of sodium and 1.2 moles of water. Okay, you already have a balanced equation and you're given absolute amounts of reactants. The question should be, which one runs out first? Which one is limiting? So how do we find out the limiting one? We assume that all of this one is used up and convert it to that one using our conversion factors. Then we assume that all of this one is used up and convert it to that one and compare the values. The one that produces the least amount is the limiting one. That's the one that runs out first. So this requires that sodium, we're going to convert it. We need sodium on the bottom, hydrogen on the top. So this is a 1, this is 2, and that makes 2 moles of hydrogen. Oops. Not water, hydrogen. Okay, so there's our first conversion. The second one is converting water to hydrogen. So the coefficient of water is 2, coefficient of hydrogen is 1, and this makes 0.6 moles of hydrogen. Okay, so now we know which one's limiting. That one makes the least amount, it runs out first. This is limiting. This is excess. Okay? Now, did that answer the question? Matter of fact, it did.
Why did you put 2 in there and only 1?
Coefficients. 1 and 2. Is that what you're talking about?
Yeah.
Okay, that's your conversion factor. And conversion factors in these problems always come from coefficients.
Yeah, I thought you were doing both of them, and the one on the same side. So I thought it was going to be a 2, but I see what you did.
Oh, no. That approach is possible, but it really is difficult to interpret. It's easier to interpret the results of limiting versus excess if you convert both of your reactants to one of the products, right? And since we need to know what this is, we pick that as our product. We could do the same thing, you know, find out how much sodium hydroxide is made and compare the two. And that would tell us which one is limiting, but it would add another step to the process of finding out what that is.
I don't understand this. You said a smaller number is 11.
Right, it's the one that runs out first.
Oh.
Yeah. So what you're going to do is you're going to use up all of this one and produce this much hydrogen. Okay? And in the process, you're going to use up some of this. How much of this are you going to use up? 2 to 2? They're 1-to-1 ratio, right? So you're going to use up exactly the same number of moles of sodium as water. Right, so you got that many sodium to start with, but you're going to use up 1.2 moles. So you're going to have 2.8 moles of sodium left over. Right? It's 1-to-1. You're going to use up the same number of moles of sodium as water. So this is excess. You're going to leave that much behind. That's another way to interpret it. You could do this calculation, say, okay, you could assume that this one is limiting, use all of it up. How much of this one are you going to use? You're going to use that much, so that's the excess. That would answer the question also.
So what's the answer?
The answer is here. The question was, how many moles of hydrogen are produced? Okay.
So why did you have to do the top?
Which one? This one?
Yeah.
Because only by comparing the two will you know which one's limiting, which one's excess.
So you picked the one.
Right. The limiting is the one that produces the least amount of product. Well, that was 3. Maybe we ought to do another one that talks about limiting in excess. Let's see, what do we have to choose from here? Nope. Ah, what about this one? Number 6. 6 is a little more complicated, but it's still working on the same premise as number 3 did. Okay, the unbalanced equation is where we're starting here, so that means you got to balance the equation. So we're going to take ethanol, right, in the gaseous state, heated up past 70, about 76 degrees centigrade, I think, is the boiling point of ethanol. And combine it with oxygen, and you get carbon dioxide and water. Okay, so let's balance that one. We'll do it the systematic way. Okay, we've got carbon, hydrogen, and oxygen. Yep. So on this side we have 2 carbons, we have 5, 6 hydrogens, and we have 1, 2, 3 oxygens. On this side we have 1 carbon, we have 2 hydrogens, and we have 3, 1, 2, 3 oxygens. Okay, remember we save oxygen for last because it's elemental. If we put a coefficient in front of this one, it only changes that one, so we hold it till the last. So let's just start with the top, carbons. If we need 2 carbons on this side, do that. But that also gives us 4 oxygens plus 1 is 5. Okay. Now we need hydrogens. We've got, still have 6 hydrogens over here, and we need 6 hydrogens here, so we get 3 there. Okay, but that gives us 3 oxygens plus 4 oxygens is 7, right? Okay. Now we need 7 oxygens on this side. So how do we get 7 out of it? How do we get an odd, huh? Okay, if we put a 3 there, that makes 6, plus 1 is 7. Okay, now we're balanced. 1, 3, 2, and 3. All right, now that we've got a balanced equation, we can look at the other information that's given. And it says, you start off with 1.70 grams of ethanol, okay, and 11.2 grams of oxygen. Okay, so this must be in an enclosed vessel. Because if you did this out in the open air, that would be excess automatically. You're not going to run out of oxygen. Okay? So it has to be an enclosed vessel, which is doesn't matter for the solving the problem. I'm just making the point. All right, so you're given absolute amounts of both. So that means one of them's going to run out. It's very rare that you would have a stoichiometric ratio of 2. Remember that name, stoichiometric. It means you have exactly the amount you need here and here so that they're both completely used up. Nothing left over. That rarely happens. So we're going to try to find out which one is the excess. And we can't go from grams here to any of the products, right? It has to be numbers, it has to be moles. So we've got to find out what's the molar mass of this, because that's our conversion factor for ethanol. That's how I read, that's my abbreviation for ethanol, okay? ETOH. You might see that again sometime. But that's this molecule right here, ethanol. Okay, we got to convert that to moles. So grams here, grams on the bottom, moles on the top. So whenever you see a quotient of grams and moles, think molar mass. So we need 2 carbons. We need to do that. And we have 6 hydrogens. And we have 1 oxygen. So just add those up, get our molar mass. So that's 24.02 and 6.0, oops, 0.06. Okay. And 16. is 4608. Okay, 4608. There we go. Grams cancel. And divide that into 1.7. I get 3.69 times 10 to the minus 2 moles of ethanol. Okay? So let's do moles of oxygen now. So we have 11.2 grams of oxygen. So what's our conversion factor for oxygen? What's the molar mass of O2? Times, right, 32. There we go. So grams cancel. And 11.2 divided by 32 is 3.5. 0 moles, that's not right, times 10 to the minus 1 moles of oxygen. Okay. Now we can convert them to one of the products. Well, that begs a question that I forgot to put up there. How many moles of carbon dioxide are produced? So we're going for this one. So it makes sense. If you need to convert to some product to find out which one is limiting, why not go for the one that gives you the answer? Okay? I mean, we could answer the question of limiting using that one just as well. But we need to know this one, so let's go for that one. So let's convert this one to that one, and convert this one to that one. Right? Now all we need is the coefficients to go in here. 2 for CO2 and 1 for ethanol. And for this one, 2 for CO2 and 3 for oxygen. Okay. So this one times 2 is 7.3 significant figures, 3.8 times 10 to the minus 2 moles of CO2 are possible from this amount. And this times 2 divided by 3 is 2.33 times 10 to the minus 1 moles of CO2. Okay, so which one's limiting? Look at the, this is scientific notation, right? 10 to the minus 1, 10 to the minus 2, which one's smaller? Yep. So this is the limiting one. And at the same time, it gives you the number of moles of carbon dioxide. Now let's look at the answers. What form are the answers? They're in standard notation. Okay. So this would be 2 places, 1, 2, 0.0738 moles. So we should be able to find that one in the selection. And it's E for number 6. Okay?
I think how it happened. If you just look at the 2.33, I love how they got that. Like I was thinking. In case you're like looking at the other one, you're like, oh yeah, I got the numbers right.
Oh yeah. Yeah, that's a common practice in multiple choice. You know, the right answer's in there, but they're going to give you several wrong answers because they know how the mistakes that students will make in calculations. So they say, okay, if they make this mistake, they're going to get that answer. Let's make that one of the selections. So you can't just find the one that you got and think it's right. You have to do it right to find the one that's right. Okay, that was number 6. A limiting reactant problem which was much more involved than the first one. Let's see what else we can find in here. Skip along, hop along. Well, a lot of them that follow that same pattern. What about something like 14? Those kind of questions. Which of the following statements is true? Those kind of questions have a tendency to spin your head around backwards. So look at the following equation. Aluminum hydroxide plus hydrochloric acid, probably. It doesn't give the states, you know, what state are they in, so technically you could say hydrogen chloride. Oops. And that one died. Try something else. Try blue. See if it works for a little while. Not very promising. Water and aluminum chloride. I don't like that one either. See if this one's got any life left in it. Okay. Suppose that 0.55 grams of water are produced from 1.2 grams of aluminum hydroxide. And a certain amount of this one. We don't know how much. Which of the following statements is true? Okay. Now, the reason it says choose the best answer is there might be more than one correct answer, but one is more right than the other, as they say, or truer than the other. Okay, so the first one says aluminum hydroxide is not the limiting reactant because we are given an amount of leftover aluminum hydroxide. Are we given an amount of leftover aluminum hydroxide? I don't see it. It doesn't say there's leftover, right? So that one's false. How about aluminum hydroxide is the limiting reactant because 1.2 grams of aluminum hydroxide produces 0.55 grams of water. Can we say that this is limiting? Not necessarily. What if there is a small amount of this one and that gives you this and there's excess here, right? So the second one's false too. Because the information is not there to justify the statement. That's the whole point there. How about C? Aluminum hydroxide is not the limiting reactant because more than 0.55 grams of water could have been produced from 1.2 grams of aluminum hydroxide. Okay, the only way to answer that one is to do the calculation. So we have to take 1.2 grams of this and find out how much water would actually be produced. So 1.2 grams of aluminum hydroxide. How many moles is that? Grams here, moles there. So we need a molar mass of aluminum hydroxide. 26.91 for aluminum, and 3 oxygens, and 3 hydrogens. Okay? And now I put that down. I've only got 2 hands. Sometimes I like to have more than 2. And so I get 77.94. Okay. So how many moles of aluminum hydroxide is that? Well, we divide that into 1.2, and I get 1.54 times 10 to the minus 2 moles of aluminum hydroxide. Now we need to convert that to water to see how much water would be produced from that much aluminum hydroxide. Okay. So we need a conversion factor to convert to water. And that would be what? 1 on the bottom, 2 on the top. Those are the coefficients. And that gives us 3.08 times 10 to the minus 2 moles of water. Right? Well, we're not there yet because we can't compare moles to grams. Right? So we've got to convert back. Got to convert this to grams by canceling the moles. What's the molar mass of water? You remember? (16 plus 2 times 1.01 for the hydrogen. So 18.02 times that one is 0.55 grams of water. All right. So let's go back to the question. Aluminum hydroxide is not the limiting reactant because more than 0.55 grams of water could have been produced. Now that's stoichiometric, right? So that one's false too. That means the answer I've got in the key is wrong. Unless it's the best answer. Let's look at D and see if it fits. Because this says, C says it's stoichiometric. So D, aluminum hydroxide is the limiting reactant because it has a smaller coefficient than, no. Coefficients have nothing to do with that. The absolute amounts that you're given is where you start and end with limiting reactants. So that one's false. How about E? There's not enough information given to answer this question. That probably would be the best one, but it's not really a good answer. Right? So there's really no good answers in there. I don't know how I came up with C. Probably the authors of the question gave me the answer and I just accepted it. Let me see what I say in here. Maybe I can explain it by looking at what my thought processes were several years ago. I may have did I make a conversion error? 78? I did. Let's look at this again. This one right here. Aluminum is 26.98. That's it. That's why C is not stoichiometric. Because I miscalculated here. So that's a 9. 9, 6, 8, 2. So what would that be? 26.98. 3 times 16 is 48. And 3.03, 7801. Okay. Yeah, how easy it is to make a mistake.
That's what I do all the time. One little digit out there.
So this replaces that number, 78.01. Divide that into 1.2. And that's, this is, let's hold on to our, is that right? Do it again. .538. So let me not throw away any decimals yet. We got that many moles of aluminum hydroxide. Is this balanced? Aluminum, 3 oxygens. I don't think it's balanced. That's the problem. That's the problem. But the question said it was balanced, didn't it? The following reaction. It appears to be balanced because it has coefficients. But we better check that. And see. So 1 aluminum, that's good. 3 chlorides, that's good. 3 oxygens, that's not good. There's 3 oxygens. And 6 hydrogens. There, that needs to be a 3. Three in front of the water. Okay. That means this needs to be corrected too. This would be 3 here. Okay. 7803. Did I do that? Okay, so that's right. That needs to be more. Okay. There may not be a right answer in that after all these mistakes. So now, that's correct. This is correct. This is times 10 to the minus 2. Okay. So now, what do we get in here? 1.538 to the negative 2. And now this is going to be 3. Okay, so 3 times that gives you 4.614 times 10 to the minus 2 water. 1802, that's correct. And this turns out to be 0.831. Standard notation. Grams of water. All right. So if all of this is used up, we should have 0.831 grams of water, but we don't. We only have that much. Right, so what does that mean? That means this is excess, because it would make too much. That must be the limiting one. and this one's excess. Everybody see that? If we used all of this up, it would make 0.8 grams. But the problem says we only get that much out of it. So it can't be all used up. Only part of it can be used up. That means it's excess. And that one is the limiting one. Now, yeah.
The 3 in front of the H2O is 2.
Well, I rebalanced it. Yeah. Let's check it to be sure again. 1 aluminum, 3 chlorides. 3 plus 3 is 6 hydrogens. 2 times 3 is 6. And 3 oxygens. 3 oxygens. That's the problem. It's not balanced in the problem. Okay, so we've established this is limiting, that's excess. Now let's go back to our questions. Aluminum hydroxide is the limiting one. No, it's not. So these are still false because it's not limiting. Aluminum hydroxide is not limiting, C, because more than 0.55 grams of water could have been produced. That's why this one's true. We could have gotten more water. So this one's not limiting. So the answer is correct. The problem was written wrong. I don't know who to blame for that one. Maybe I transposed it wrong. Or maybe the way they do these question banks and the way they do all homework problems, they hire a third party to do them. Maybe they've got a graduate student who needs money, or teaching assistant. They pay them a little extra to do these things, and they make lots of mistakes. The editors are supposed to catch it, but they don't always do. And these problems have been out for, I don't know, 6 years. So they don't care now. They got a whole new set they're working. Okay, any questions about 14? Besides the fact that it was set up wrong? We fixed it. That was your critical thinking lesson for today. I'm glad we took that one, because I never would have caught that mistake if we hadn't tried to actually work it out. Come up with initially what was the wrong answer, but we discovered that it was the right answer. It's just we couldn't prove it from where we started. We had to fix it first. Okay, that was 14.
So the reason the thing that messed us up is we assumed that it was balanced.
Correct. That was a huge assumption, and we all know what assumption means. When you assume, right? Does everybody know what assume means? Okay, I don't have to explain. Let's see. And let's move on to that one. How about 18? Switch gears just a little bit. How many atoms of aluminum can be produced by the decomposition of 31.5 grams of aluminum trioxide? Aluminum oxide, actually. That's a type 1 compound. So all we have to say is aluminum oxide, because aluminum can only have one charge. Oxide only has one charge. So write the balanced equation first. That's the hint. When we decompose aluminum oxide, what happens? Compound to elements. That's what we're saying. We're not given any other information. So when you hear decomposition, and that's all you're given, assume that it's going to elements. So we're going to have aluminum plus oxygen. Okay. In standard state. That's the elements that will show up. So now we need to balance it. We need two aluminums. Since they're both elements, we don't even need a table. We need 3 oxygens. So that gives us 3 oxygens. But now, what do? Get rid of the fraction. So now we have 2 aluminum oxide and 4 aluminum metal and 3 oxygens. Okay? We use the fraction trick. Now that we've got the balanced equation, we're starting off with 31.5 grams of aluminum oxide. The question is, how many atoms of aluminum? So how do we go from there to there? You can't do this, because that's not moles. You got to convert it to moles. We got to convert grams to moles. That means we need molar mass. Let's see if I can do this without making a mistake this time. 26.98. Right, 2 of them, and 3 oxygens. Now, .98 times 2, and then 48 added to it. 101.96 grams per mole. So we divide this into that, and I get 0.3089 moles of aluminum oxide. Okay, so now we need to convert. Now that we've got moles, we can go from here to here. We just need a conversion factor. Okay, so that comes from where? Coefficients. We have 2 of these, 4 of those. That's just 2 times that number, right? 0.6179 moles of aluminum. Okay, not quite there yet, are we? Because the question is, how many atoms? We need another conversion factor. Moles to atoms. So what's the magic number?
6.022 to the 23rd power.
There you go. So Avogadro's number gives us 3.72 times 10 to the 23rd atoms. Now let's see if that was one of our selections. Yeah, it turns out to be A. So, where are the stumbling blocks in this problem? Writing that equation. That's the first place that can throw you off. So when it says decomposition, you need to know, without any other information given, decomposition means make elements out of it. Okay, then balance it. So that should be, you should be able to do that one in your sleep now. Then, where's your starting point? Well, your starting point is mass, so it's got to be moles. You can't go anywhere in a balanced equation unless you've got moles. So we convert it to moles. And then we say, okay, that many moles of aluminum oxide makes how many moles of aluminum? And you're still numbers. Moles is numbers, but it's not the right numbers. The units of measure are atoms in this case, and not moles. So it's just a unit conversion from moles to atoms. And you're done. Okay, that was 18. Anybody think of one that's just burning, except for 76? We're gonna get that one for the. Let me take a look at 76 and see if we've got enough background information to jump straight into that one. Let's see, here we got an ABC problem. Okay, let's do that. So we'll move it from holding pattern to flight line to take off. And this one's dying. Let's see, 76. Consider the equation A plus 3B yields 4C. And you're given 3 moles of A is reacted with 6 moles of B. Okay. Which of the following is true about the reaction? Well, alarm bells ought to be going off in your head right now. You're given some of this and some of that both. So one of them is probably going to run out. So let's find out how much, in anticipation, let's find out how much C could be produced from each one. They're already in moles. So all we have to do is say 3 moles of A equals how much C. So A is 1, C is 4, right? So that would produce 12 moles of C. 6 moles of B, on the other hand, 5 fingers, 3 and 4, right? 3 B's, 4 C's. So 3 into 6 is 2 times 8 is, times 4 is 8. Okay, so this one's limiting, and this one's excess. All right, now let's look at the questions and see if that helps us. For A, B is the leftover reactant because you have more moles of B than A. Well, no, B's not left over at all. B's limiting. B runs out. So you don't even have to consider the rest of that statement. B is left over, again, false. There's no B left over, it's limiting. What about C? A is left over, now that's true. We do have some A left over, right? Because for every 1 mole of A, 4 moles of C are produced. That's true, but that doesn't support the statement that A is left over. This is a true statement, but what really determines which one's limiting or not is the absolute amount that's given for each one, not the ratios. The ratios are used to find out which one is limiting, but that doesn't dictate which one is limiting. The coefficients are simply conversion factors. To find out which one's limiting, you have to use those plus its information. So that's why C is false also. D, neither reactant is left over. It's not stoichiometric. That's false. A is left over. Okay, it's excess, that's true. And why? Because you need only 2 moles of A and have 3. All right, let's see if that's true. You need 2 moles of A and you have 3. Is that true? Do we only need 2 moles of A? Right. So how would you find out how many moles of A you need? Right, we didn't do that calculation yet. You take, you know this is limiting, so you take 6 moles of B and convert it to A to find out how much of A you need. So B is 3 conversion, A is 1, 3 and 6 is 2, times 1 is 2, 2 moles of A. So that's how much you need to react with 6 moles of B. Is that true in that statement? You need only 2 moles of A, but you have 3. E is true. Okay? As it turns out, to answer the question, we didn't need to do this. We could have just done that calculation. But, well, no, I take that back. We did need to know that information to answer these questions. But when we got down to E, that didn't answer E. We had to do an additional calculation to prove E. Okay? That was no good either.
Well, I can quite a pile of it.
It's cathartic. Throw stuff around. It's better than kicking your dog or punching your wife. Or your husband, as the case may be, right? Okay, any questions about that one? How we answered each one of those questions? Okay. Let's see here, let's try this one. That was 76. Trombones. Let's see. We could do that one. We've done that one already. A lot of repetition in this review document. Did anybody get all the way through? And probably not. Or do you just take every even or every odd? That's the way to do it. If you've got a huge review document like this, and you're limited on time, just go through and take every other one or every third one to make it all the way to the end. Because usually they're bunched. You have a certain type up here and a certain type down there. You want to be sure and be exposed to each type of problem all the way through. And then if you have time, you can go back and hone up on the ones that you had struggled with. Let's see here. Move the back and work forwards. Let's go to the very last one. I know we've done this type of problem, but I think we've touched on every possible type of problem so far. So now we're just getting practice. 87. Last one in the bunch. I see the handwriting on the wall there. Let's try this one. You know what they need to do with these? Have you ever cut one of these open? You find that it's packed with felt all the way to the top, right? That takes up space. Right? There's only so much stuff you can put in there that writes, so much ink. So why don't they just pack the tip with the felt and fill this up with liquid? You know, that gives you more capacity. Just an idea. They wouldn't be able to sell as many. So think like a businessman and say, oh no, we need to make more money.
Yeah, you're thinking like a scientist.
Mm-hmm. That's too logical. Okay, consider this reaction. That one, which is metal, reacted with this one. Uh-oh, I know where this one's going. We're going to make rust. There you go. Did I ever tell you about the Omni building in Atlanta? No?
You did, I
Yeah.
can't remember what they said.
The one that was covered with steel that rusted like that
Because they
and
saw.
sealed the surface?
Yeah.
Okay, I told you that one. Okay, so let's back to the problem. Is this one balanced? We better be sure. 2 irons, 6 oxygen. Oops. That's only 3 oxygens. 2, 3, 3, 3. It's not balanced. We better balance it, right? So 2 irons, yeah, that's right. But we need 3 oxygens. Like that. Now we need to do this. Something tells me that answer's not going to be right. So 2, that's 4 irons plus 3 oxygens yields 2Fe2O3. 4 iron, 6 oxygen. Now we're balanced. All right, let me see what kind of damage that's going to do with my work problem. It's a mess. Make a note. Fix it. See, that should be 4, 3, and 2. 4, 3, 2. So I have to go fix that one. All right, so now let's work it out. Push that aside. We got this balanced equation and 11.9 grams of iron 3 oxide. Is this iron 3 oxide? That's minus 2 minus 6 minus 6 plus 3 plus. Yep, that's iron 3 oxide. 11.9 grams. Is produced. How many grams of oxygen are needed for this reaction? So the question is, what mass of oxygen is required? So how do we get there? Got to make moles first, don't we? So let's convert this into moles so we can go back over here, right? Because there's a great wall there. Can't get over the wall without moles. That didn't sound right. Can't get under the wall without moles, right? I have to change my analogies. So we need the molar mass of this one. So that's 2 times iron, 5585. And then 3 oxygens. There we go. Now let's do a quick cipher here. Jethro could cipher the numbers. Made it all the way through the 6th grade. And mole. Okay, so this is 159.70. Divide that by this number. 7.451 times 10 to the minus 2 moles of Fe2O3. Now we want to find out how many moles of oxygen there are required to produce rust. Then we can go back and calculate mass. So we're going to start off with 10 to the minus 2 moles of rust. This one's running out too. So our conversion would be from rust, which is 2, to 3 oxygens, would give us 3 times 2 divided, would give us 1.118 times 10 to the minus 1 moles of oxygen. And now we just need to convert that to grams. Grams over moles, molar mass of O2. Right, we did that earlier. 32 grams per mole. So 32 times this is 3.58. So that's how much oxygen is required. And I wonder if that answers, it is there. Turns out to be D and not E. So we've got to change that too. D. Because this needs to be, what was it, 432? 432. Okay? While I'm thinking about it, I'm going to check the exam to see if that problem snuck in here somehow. Look at that equation. Nope, it's not there. Okay. How are we doing on time? 9:15. We go to 9:40, don't we? Okay. Okay. Are there any others in there? I can start making them up as we go along. Starting to run out of markers. What if we react an element with fluorine? I'm just making this one up so it has no number. There's our element. We react it with fluorine. Doesn't have a number. Doesn't have a number. I don't think it does. Maybe I'll look and see. Maybe. I didn't think of that. That's in here. Then you have a reference point. Coming in on the fluorine, that should stand out. So far, nothing. Nope. This is freshy. So the ratio is 3:6. Like that, I think. Yep. Okay. So the X is unknown. We want to find out what X is. X reacts with fluorine to give you that XF6 compound. And we know that we started off with 235.2 grams of this one. Okay? So we weighed that one out, then we reacted it with fluorine gas, and we weighed the product, which is XF6, 347.9. Okay? So the question is, what's X? What do we need to know to find out what X is? Well, it'd be nice if we knew the atomic number. Right? Can you get the atomic number from that? No. You gotta know how many protons, right? We're not given enough information to find proton. But as it turns out, the protons from upper left to lower right get bigger, right? The atomic number gets bigger. Also, the mass, the molar mass of the element gets bigger from left to right. And it's fairly unique for each one. There's significant differences between each step that you take between. Some places they get really close together, so experimental error could overlap between two. And then you might need another bit of information to break the tie. But usually, if you know the molar mass of an element, you can find out what it is. So let's assume that's okay for now. And say, what do we need to know the molar mass of X? And MW is molecular weight. Molar mass. What do we need to know? We need to know grams per mole, right? That's molar mass. So we got the grams already, right? Right there. Now we need to know the moles. How many moles of X does that represent? Okay. Here's where it takes a little detective work, because we cannot convert that to moles because we don't know what X is, right? But we know this mass and that mass, and the law of conservation of mass tells us that you can't create mass and you can't destroy mass. So where did this extra mass come from? Right there. Right? So we just need to say 347.9 grams minus 235.2 grams is equal to 0.7211 grams of fluorine. 112.7 grams. Right? Because if you add these together, it better be that much. Right? So now we know how many grams of fluorine there are. We can find out how many moles of fluorine and then figure out how many moles of X. Okay? That's the trick to this problem. Finding out what that is. After you do that, the rest of it is just same as everything else. So 112.7 grams of F2 is how much X? Well, actually, we need moles first. Right? Grams, moles. So F2 is going to be 19 times 2 is 38. So we divide 112.7 by 38. 2.97 moles of chlorine. Now we can find out how many moles of X. So the ratio is 3 to 1. 3 to 1. When you 3 times 3 divided into that one, pretty close to 1. 0.989. Now we got moles of X. So we say molecular weight equals grams, 2 grams per 0.989 moles. 235.2. 238. 238 grams per mole. So you just look on the chart, see if you find something that's close to 238. It's going to be down here close to the bottom, isn't it? How about uranium? Okay. We identified the unknown. Think you can reproduce that? You give them this, all right, so that's good. You give them that, you give them that, you know, that's good. You know what you need to find. You need to find the molar mass to identify the element. Right? You already have part of it. You just on a detective hunt for the moles. So the real trick is remembering conservation of mass. That minus this equals that. And from then on, you just use the stoichiometry of the equation to find out how many moles of X there are. Okay? Any others? Let's see, maybe I can come up. Did we do percent U? We haven't done that. Okay. Never mind. We might get to it. Well, I'm exhausted. In other words, I have no more ideas.
I just have one question
Mhm.
about this one.
Okay.
So with the X, is that considering that there would be no coefficient or anything like that to the element?
Well, there is one. There's one.
So that is it. So
Yeah.
there is that possibility that with lumped in with the mystery of X, there's also a coefficient.
Oh, I see.
Sometimes people
A
when you
hidden
put X,
coefficient.
yeah, sometimes when you're supposed to find out what the coefficient is, but with the X we're considering it is one, then all of that makes sense to me now.
Yeah.
That's what was confusing me, because if you bring into question whether there's more than one of the elements, then
Right.
throws everything off. But now it makes sense.
Okay. I see. X here represents an element symbol.
Just the element.
Right. It's not an unknown X with something that might be X equals to something else. It's like maybe that X equals 3Y, and Y is what you're looking for. Yeah, no. We have to assume that X is only one of them.
Yeah, like I said, it makes a lot of sense now. I was thinking throughout there, but you could, if there was more than one element, it would throw off the molar mass so much
Right.
that it would be completely different.
And this,
But like I said, it makes sense now.
and this is a real process. When uranium is separated into fissionable and non-fissionable fractions, they convert the metal into the fluoride, which makes it a gas. Then nowadays they use ultracentrifuges. So you can take that gas and run it through the centrifuge and separate the U-238 from the 235, different masses. It takes several thousand centrifuges and stacked in a row to do it, because the enrichment is just minuscule for each step. But that's the way they do it. They make it into the fluoride. And this uranium fluoride, hexafluoride, is extremely corrosive, right? So your centrifuges have to be designed so that they're resistant to that corrosion. My guess is that all the internal parts are coated in Teflon, because even stainless steel won't hold up to that. It'll just eat it right up. And then once you've separated the U-235 from the 238, then you take this and you decompose it, right? So then you get your uranium back plus your fluorines back. You got your uranium metal. And you be sure you don't put too much of it together in one lump. Otherwise, it'll go kaboom. So that's what I'm hoping for the Iranian. You know, they make a mistake like that. They put too much of it together in one place, and it just completely obliterates their whole facility. Yeah. And most of their stuff, well, all their important stuff is underground, right? They're hiding it underground. So what we would get is maybe a reading on our seismometers all over the world. And they can pinpoint with the seismometers, where did that happen? Oh yeah, it's right there where that unknown facility is located.
What would be the point of condensing down uranium like that?
Of doing what?
What would be the point of condensing down uranium to 235? What was it used for?
Oh, 235?
Mhm.
That's the one that fissions. So if you get enough of that together, you make a bomb.
Oh, okay, that's great.
Yeah, it has to be extremely enriched, like maybe 95% of this. And you have it non-critical, subcritical masses separated. And then you put one up here at this end of this tube and one down here, and you use a explosive charge and you fire it down there, and when it hits, it goes critical and big boom. That was the bomb that hit Hiroshima. Little Boy was a uranium gun type reaction. That's why Little Boy is that long, thin one, right? Fat Man was made with plutonium, right? Plutonium. Here it is. I'm not sure which one is fissionable for plutonium, but you couldn't use a gun type to make plutonium go critical. You had to use the same type of procedure they used at Trinity for that test. That was not a uranium bomb. That was a plutonium bomb that blew up the first atomic bomb that went off. And in order to do that, they had this sphere, a hollow sphere of plutonium, the fissionable isotope. And then they had positioned around it panels made out of C4 or something like that, the high explosive. And then they also had another sphere around that, and then they timed it so all of those explosions went off at once. So they exploded out, plus they exploded in. They compressed the sphere down to a critical mass, and that caused it to go off. If you try to gun type with plutonium, it'll fizzle. All you'll get is just the high explosive reaction. You won't get it. That was the solution to the problem of using plutonium versus uranium. Because plutonium is a byproduct of the uranium. Forgot my terms now. If you stick 235 and 238 together, where 238 is a lot lower concentration, and you put it in a reactor, control reactor, like you're making power, then over time, one of the products is plutonium. So you clean out the pellets and you separate them out, convert them into fluoride, separate them out and isolate the plutonium, and then you can make a bomb. They're called breeder reactors. They make more fissionable material than you started with. Shoot. I hate it when I can't remember terms like that. Okay, so we're done. Let me stop this before I continue.